Good morning, students. My name is CH.S.V.PRASAD, and I am working as senior lecturer in electrical engineering, Government Polytechnic, Yadgirigutta. Today, we will start the uh, lesson AC motors. Already we started. We will continue in that one. In this subject, we will start the chapter, continue the chapter synchronous motor. In this chapter synchronous motor, in the last class we covered different types of torques in synchronous motor. What are the types of synchronous motor torques we have? As I told in the last class, we have four types of torques. One is starting torque. So the name only it says it is produced at the time of starting. So when the motor, synchronous motor is connected to the supply, then it develops a start torque which produces the rotating magnet field, or it will start the rotor. At the time of starting, when we give the connection to the synchronous motor, the torque produced at the time is called starting torque. Starting torque. So next one is second torque is called pull-in torque. That is when the synchronous motor is pulled into synchronism. That is magnetic locking between stator rotor poles and stator magnetic poles. That is called the motor pulls into synchronism is called pull-in torque. That is the motor is pulled into synchronism is called pull-in torque. So when we give the supply to the, so how it is produced pull-in torque, how the rotating magnetic field is produced in stator, that one also we derived in our second class or third class. At the beginning, when we give a three-phase supply to a stator winding, then it produces a rotating magnetic field whose magnitude is 1.5 times the maximum flux, which is rotating at a synchronous speed. So that means, so when we give the rotor, so that means it is rotating at a synchronous speed and its magnitude is 1.5 times the maximum flux. At any instant, if you take at 0 degrees, 30 degrees, 60, 70, 60, 90, any degrees, 150, 180, 270, 240, or 300 or 360, at all the instants, the resultant flux is 1.5 times the maximum flux. And it's rotating at a synchronous. That means the stator also produces a magnetic poles, that is north pole and south pole, and that pole also rotating at synchronous speed. So to start the motor, what we have to do, we have to rotate the rotor near to the synchronous speed, so that, and we have to give the DC excitation to the rotor winding. Then what happened, because of DC excitation, the rotor poles gets powerful magnets, and it lock the stator magnetic poles. That is, both will get magnetically locked each other. Then what happened? Both will start rotate at a synchronous speed. So at that time when the motor pulls into synchronism, that is the magnetic locking between rotor poles and stator magnetic poles is called magnetic locking, and at the time the torque produced is called pull-in torque. Okay, when it is pull-in torque, the synchronous motor starts rotating at a synchronous speed. If you apply the load, then also it starts running at a synchronous speed only. So at the time the torque, so at the time the torque produced is called running torque. So what is the torque? The torque produced when the synchronous motor is running. At the time the torque produced is called running torque. So that is the third torque. First one is starting torque, next one is pull-in torque, next one is third one is running torque, next fourth one is pull out torque. So this torque is the max maximum torque the motor can withstand. After that, the motor comes out of the synchronism. That means if you apply the load, the motor will bear and runs at a synchronous speed. If you apply more load at particular instant, then what happened? The motor is not possible to bear any load. At that time, the motor comes out of the synchronism and the motor stops. So when it happens, so when you apply the load, then what happens? The load angle or coupling angle, that is the axis of rotor and the axis of stator, will have some phase difference, that is called load angle or coupling angle. If you increase the load angle increases. When load angle increases, back EMF increases. When back EMF EB increases, then armature current IA increases. And this will produce a more torque which bears the extra load which is connected, which is applied on the motor. So again if you increase, again alpha increases, EB increases, armature current IA increases, then torque increases. But at particular point, that is the maximum point, when the alpha is, the alpha increases. So when the alpha value reaches 90 degrees, then the motor comes out of the synchronism. That means after 90 degrees, if the angle increases above 90 degrees, what, above 90 degrees, then motor stops. So there are four types of torques: starting torque, pull-in torque, running torque, and last one is pull out torque. So that means the motor can bear the load, it can bear the load, it can bear the load. At particular instant, when you apply the load, alpha increases, back EMF EB increases, then armature current increases, then torque increases. So the process will continue until it bears the load. So alpha also increases. At what one particular point, the motor is not able to bear any load. At that time, the motor comes out of the synchronism and the motor stops. So the torque where the motor comes out of the synchronism is called pull out torque. Pull out torque. So at what angle this will happen? This will happen when alpha is equal to 90 degrees. That is the maximum power or maximum torque the motor can bear at that time. So when below the 90 degrees, when alpha is below 90 degrees, then below 90 degrees. Then motor is in synchronism and runs at a synchronous speed. So runs at a synchronous speed. So when the alpha exceeds above 90 degrees, exceeds above 90 degrees, then the motor stops and comes out from the synchronism. The torque available at that point, when alpha is the you can define as like that. When the motor comes out of the synchronism is called pull out torque, or the torque available when alpha is equal 90 degrees, then also it is called pull out torque. So we have four torques we covered in the last class: starting torque, pull in torque, running torque, and pull out torque. And we derived the and we done the problems on torque also. So today we will see the effect of excitation on armature current and power factor under normal excitation, under excitation, and over excitation. So that means, so effect of excitation, that means if you change the excitation of the motor, then what happened? How the armature current and power factor changes. So how the excitation is changing? We are changing as a normal excitation, under excitation, and over excitation. That is over excitation. So when synchronous motor load is kept constant, then what happened when the load is constant? The input power drawn from the supply is constant. That is root 3 VLIL cos phi. So when load is not changing, the motor is not draw any extra input power from the supply. So where V is the applied voltage and input, since the applied voltage V is constant and input power is constant, then what happened? See here, P input power P is equal to root 3 VLIL cos pi. P is equal to input power is equal to root 3 BLIL cos phi. Where when P is constant and V is constant, what is the variable we have? I into cos pi. I into cos phi. How it will changes? When P is constant, when whole the right hand side of the equation also constant. So when it is happened, when both are inversely proportional, I and cost, that means the product of current and what is caused by power factor, the product of current and power factor caused by is constant. So that means the product of I into cos pi must be constant. Then only the input power is constant. So since the applied voltage V and input power are constant, I cos pi, the active component of current, is also constant for constant load. Here, what we are doing, we are not changing the load. The load is constant. When load is constant, input is constant. So by putting these two parameters, input constant and the load constant, we are changing the excitation. So when we change the excitation, then the product of Then current varies and cos phi also varies. But the product of I into cos phi is constant. Understood? So the product of I into cos phi is constant when you change the excitation. So by how we are changing the excitation? We are changing the excitation. Normal excitation. Then what is the here we will study by keeping load as constant, then the power input also constant. So then what happened if you change the excitation, then power factor changes, current changes. So but the product is constant. I into cos phi is constant. How you both are constant? So that means if power factor is increases, current decreases. If power factor decreases, current increases. So that means the product I into cos pi is constant. The product of I into cos pi is constant. So both are changes, but both are inversely proportional I into cos pi. That's why the product is constant. When product I into cos pi is constant and supply voltage V is constant, the input power also constant. So let us see how the current and power factor changes if we change the excitation by keeping load constant. When load constant, input power is constant. So when excitation is changed, the magnitude of induced EMF EB changes. So when EB changes, then what armature current changes. So but here the load is changes, the load angle alpha also, sorry, when the load here load is we are keeping load as constant. What about the load angle alpha? It is also constant for constant load. Alpha value changes only when the load is changing. When load is changing, only then alpha value changes. Here load is not changing, so alpha is constant. Understood? So next, so then what happened? The ER resultant vector depends on what is the resultant? It is a combination of supply voltage and EB. Supply voltage is EB. So that is IA into ZS. ER is equal to resultant voltage, that is equal to IA into ZS, where theta is equal to internal angle. It is the angle between ER and IA. What is the theta value? Theta is equal to tan inverse of XS by RA. So this value also constant. Why? Because synchronous reactance is constant and armature current IA is constant. Yes, as theta depends on the circuit parameter, that is Xs and Ra. So simultaneously the internal angle also constant. So where Ia is equal to armature current and Zs is equal to synchronous reactance, pi is equal to phase angle, that is the angle between voltage and current. Voltage and current. So effect of excitation. When excitation is adjusted in such a way that EB is equal to V. When we have EB is equal to V, tell me. Already we covered in the last class. When EB is equal to V, but at which excitation? It is normal excitation. So that is when normal excitation EB is equal to V. Understood? Already what we condition we taken? We taken the power is constant, the voltage is constant. Under that condition, we changing the excitation. Once again, I am telling changing of excitation at what conditions we taken? We taken when load on the synchronous motor is constant, the input power P is equal to root 3 VLIL cos pi drawn from the supply rolls, supply also constant. So since input power P and supply voltage V are constant, so then what happened? The product I into cos pi also constant. But these two changes, current changes, power factor changes. How they are changes? They changes such that the product I into cos pi also always constant. That means both will changes inversely proportional. If current increases, power factor decreases. If power factor increases, current decreases. That means change in power factor causes the change in current. That is, increase in power factor causes decrease in armature current and vice versa because the product I into cos pi remains constant. So, when excitation is changed, the magnitude of induced EMF EB changes, where load angle alpha remains constant as long as the motor load is constant. Understood? So, let us consider synchronous motor with constant load, and when excitation is changed, you are changing the excitation at some particular value. EB is equal to V. This condition is called normal excitation. When EB is equal to V is called normal excitation. Normal excitation. So if you draw the figure, it shows armature current IA lags the supply voltage V by an angle pi. See here how you can draw the, this is a voltage vector OA we have draw, OA we have draw, then we can draw a current, we draw a current lagging the voltage, current is lagging the voltage by an angle, what is the angle? Pi. Next you draw back EMF EB, EB that is denoted with vector OB, that is back EMF EB. And what is the resultant vector? ER is the, if you combination of, if you join this supply voltage V and back EMF EB, if you add supply voltage V and back EMF EB vectorially, then you can get a resultant vector ER. Resultant vector ER. This is the ER. ER. So which is making an angle of theta with respect to I. This is the theta. So this is the vector diagram for at a normal excitation when EB is equal to V volts. And power factor here, the power factor is lagging power factor only. Understood? How you drawn this one? So current lags the supply voltage by pi, and here OB represents the back EMF. OV is the back EMF which is making an angle of alpha. This is constant. Alpha is always a constant. If you add this supply voltage V and back EMF EB, we will get a resultant vector ER, which is a combination of V and EB. So this is normal excitation, where theta is a constant internal angle, that is theta is equal tan inverse of xs by a. This is one condition. So second condition is, if you reduce the excitation, then what happens? EB is less than V. When EB is less than V, when EB is less than V, then what happened? The motor is under excitation. The resultant vector ER advanced in clockwise direction. That means ER is like this, it is moved clockwise direction, and internal angle is constant. IA is moved in clockwise direction. Here you understand, EB is greater than, when excitation is reduced, EB is less than V. This is called under excitation. So at this condition, ER is advanced in clockwise direction. When ER moves, as theta is constant, IA also moves clockwise direction. Clockwise direction, IA also. So the angle pi is increased and power factor is decreased. So that means current is increased, power factor is decreased. Hence, the current is increased. So both are inversely proportional. As power factor is decreased, armature current is increased. Therefore, lower value of excitation, that is under excitation, lower value of excitation, IA increases and power factor is lagging. If you see the vector diagram, it is like this. ER is advanced in clockwise. Automatically IA also advanced. So IA value increases. Whereas pi increases, so cos pi decreases. Power factor decreases. So the product of IA and power factor cos pi is remains constant. You have to remember this one. Power factor decreases but armature current increases. This condition when happens, when this condition happens, this condition happens under excitation. In under excitation, EB is less than V. Power factor decreases and current increases. This is second condition. So third condition is when excitation is increased. When excitation is increased, then EB is greater than V. This excitation is called over excitation. In over excitation, that is EB is greater than V, over excitation, ER is moved in anti-clockwise. That is, it moves like this, anti-clockwise. When ER is moves as theta is constant, it pulls the armature current IA also, and then the motor draws leading power factor. As theta is constant, it moves current also in anti-clockwise direction, so that IA leads the supply voltage by angle theta, by an angle theta. So when excitation is increased, so that is called over excitation, where EB is greater than B. The motor is, we can say, overloaded, and ER is moved in anti-clockwise direction. As theta is called constant, IA also moved anti-clockwise. Then what happened? IA leads the supply voltage theta. So the power factor is changed and it becomes leading. So if you draw the figure, so where pi is increased, when pi is increased, power factor decreases, cos pi decreases. When cos pi decreases, as the product I into cos pi is constant, IA increases. This, therefore, lower value of excitation, lower value of excitation, IA increases and power factor decreases, but in leading in nature. That means previously IA is here, now it is. So then what happened if over excitation? In over excitation, ER is pulled into anti-clockwise direction. When ER is pulled, as theta is constant, so automatically the current also pulled in anti-clockwise. So the current I leads the supply voltage by an angle pi. So the uh, power factor, when the angle is increases, when I pi increases, automatically the power factor cos pi decreases. When cos pi decreases, IA increases, because I into cos pi product is constant. This is the vector diagram, that is above excitation, whereas EB is greater than V. This shows the vector diagram for leading power factor when the excitation is more. So fourth case is unity power factor. For unity power factor, EB is slightly greater than B. That is excitation for which power factor of the motor is unity is called normal excitation. That is IA is in phase with V. So that is current and voltage both are in phase with in phase. That is pi is equal to 0. Pi is equal to 0. Where EB is greater, slightly greater than B. This is the condition for unity power factor. Unity power factor. So if you see the all the four conditions, four conditions excitation. So this is at some particular excitation, EB is current is in phase with current. This is leading power factor. This is lagging power factor. This is also lagging power factor. So at some particular excitation, when EB is equal to V is called normal excitation. At the time, the current is lagging to supply voltage V, and ER is the resultant vector of V and EB. So at this condition, EB is equal to V. The power factor is lagging. So when current changes, the power factor also changes. How it is changes? It is changes such that the product of both current and power factor are power factor are constant. That means current increases, power factor decreases. In next condition, suppose if the excitation, so at this condition where EB is equal to V is called normal excitation. Suppose if the excitation is decreased, that is EB is less than V. So EB is less than V. So ER is pulled towards clockwise. See here, E is pulled clockwise direction. When ER is pulled, as theta is constant. Why theta is constant? Why it is the internal angle and depends on circuit parameters, that is armature current and synchronous reactance, whereas theta is equal to tan inverse of XS by RA. So when ER is pulled in clockwise direction, the current IA vector also pulled in clockwise direction. So then what happened here? Theta is pi is increased. When pi is increased, cos pi is reduced. When cos pi reduced, current is increased. If you see here, this is small, this is increased. So when under excitation, when EB is less than V, at this condition also the the product I into cos phi is constant. So this is called under excitation where EB is less than V. So when excitation reduced, what happened? ER moved to the clockwise direction as theta internal angle is constant. I also moved clockwise direction. So then what happened? Pi increases. So whereas pi power factor cos pi is reduces. When cos pi reduces, the current increases. So this is under excitation. Suppose if excitation is increased, so when excitation is increased, then what happened? Here, he see here this figure B and C. If you compare these two figures, ER is pulled anti-clockwise direction. ER is pulled in the anti-clockwise direction. When ER is pulled anti-clockwise direction, you know the theta internal angle is constant. Why? Because theta is equal to tan inverse of XS by RA. Though it depends on the circuit parameters. So automatically when ER is theta is constant, when ER is moved towards anti-clockwise, automatically the current also moved anti-clockwise. See here. Previously here it is I is towards the left hand side of the V. Now it is right hand side of the V voltage. That is current is lagging the voltage by an angle theta. Sorry, by an angle pi. So at the time the excitation EB is greater than V, it is called over excitation. So this is in over excitation EB is greater than V and current leads the voltage by angle pi. So in this case also, current increases, the power factor caused by reduces. So why? Because the product both is constant. Suppose if excitation is changed at some particular point, so that is here, if you reduced, the current is lagging. If we current excitation increased, the current is leading. So between this lagging and leading, between this one we have unity perfect, that is current is in phase with voltage. So if you change the excitation at particular point, current is in phase with voltage. At the time EB is greater than V only, but both are in phase with each other. So T pi is equal to 0. So pi is equal to 0. Why? Because both are in phase each other. At this is called unity power factor. So, so what do you understand from this? We can understand that as excitation is changes, the power factor of the motor also changes. So the excitation corresponding to unity power factor is called normal excitation. The excitation higher than normal is called overexcitation, whereas excitation lower than normal is called underexcitation, as shown in this figure. As shown in figure, that overall excitation causes leading power factor and underexcitation causes lagging power factor drawn by the motor. It can also be observed that the magnitude of current at normal excitation is minimum. If you see here, in all this case, in all A, B, C, D, where the armature current is minimum, here D. This is the minimum current what it has. What it has. So this is the minimum current we have. So by changing the excitation, so what happened when we change the excitation, the power factor of the synchronous motor changes. Either we can bring it unity power factor, we can make it over lagging power factor by reducing the excitation, that is under excitation. We can make it EV is greater than V for over excitation. If we increase the excitation and the current is minimum at unity power factor. So by changing the excitation, the current, the power factor is changes. The power factor is changes. So it can be observed that the magnitude of current at normal excitation is minimum. So, so what we can notice from this one? The magnitude of current varies with excitation and the power factor also changes. The current has large value both for low power factor, low and high value of excitation, that is under excitation and over excitation. In both case, the current is large value. Current is minimum at unity power factor. So in between we have the minimum value at particular excitation, and at that excitation the power factor is unity. So for the same input the armature current varies over a wide range of power factors. Wide range of power factor. That means if we change the excitation, we can make the motor to run at unity power factor, lagging power factor, and leading power factor. When what power factor the motor runs? The motor runs with leading power factor, and with lagging power factor, and with lagging power factor when under excitation. Under excitation. So the power factor is unity approximately at normal excitation. The power factor is decreased either in increasing or decreasing the excitation. That means if you change the excitation, the power factor changes. Power factor changes. Armature current increases with respect to decrease in power factor. Why? Why? Because the product of I into cos pi current and power factor is constant. So armature current increases, then power factor decreases. Power factor decreases. So what we have discussed now, we have discussed at this chapter, that is effect of excitation on armature current and power factor at normal excitation, under excitation, and over excitation. Once again, I will repeat this one. So here, what we consider the condition? We consider the condition when load is constant. When load is constant, then supply input P is equal to root 3 Vi cos pi drawn from the supply is constant. Since input power P is constant, the supply voltage V also constant. So change in power factor causes the change in current. That is increase in power factor, then increase in power factor, then decrease in armature current, and vice versa. That means the product I into cos pi is constant. So when excitation is changed, the magnitude of induced EMF EB changes, whereas the load angle alpha remains constant as long as the motor load is constant. So let us consider a synchronous motor with constant load, where at particular load EB is equal to V and the current I lags the supply voltage by small angle pi. The internal angle theta is constant. Why? Because it depends on the circuit parameters. That is, theta is inversely proportional to tan inverse of theta is equal to tan inverse of xs by RA. That is one condition. So suppose if the excitation is reduced, then EB is less than V. EB is less than V. EB is less than V. Hence ER is advanced in clockwise, and so the armature current also moves into clockwise direction because theta is constant. So then I increases, but the power factor cos phi decreases. So that is Second condition, and that is under excitation. Suppose if excitation is increased, then EB is greater than V. Then ER is pulled in anti-clockwise clockwise direction. When ER is pulled anti-clockwise, then armature current also pulled into anti-clockwise, and it in leading power factor, that is current leads the voltage. At that time also current increases, power factor decreases. And fourth condition, if we change the excitation such that the current is in phase with the voltage, that is called normal excitation. At this condition, the current value is minimum. So from this what we understood, that means if excitation higher than normal, then it is called over excitation, whereas excitation is lower than normal is called under excitation, and in under excitation the power factor is lagging, and in over excitation the power factor is leading. So these points we have covered and noticed when the excitation is changed. So what we they are asked frequently, they are asked effect of excitation on armature current and power factor. So you practice this one. This is the assignment for you. Explain with neat diagram how armature current and power factor varies with effect of excitation. You read this one as a assignment. I hope you understood this. You read once again, and if you have any doubt, ask me in the next class.